We're going to look at problem number 14 on the Chapter 7 WebAssign. It's a difficult one that has more than one part, and so we're going to view it in compartments. So if we look at this first line, you'll notice that they seem to be doing a titration here. They have a sample of a weak monoprotic acid and some sodium hydroxide. They tell you how much sodium hydroxide it takes to reach the equivalence point, and they tell you the volume of the monoprotic acid. So we should be able to find the concentration of the weak acid. We could either do it by thinking about equal moles, or we could do it using MV equals MV. So I'm going to plug in the numbers and see what we get. I've plugged in all my quantities, and when I calculate it, it comes out to be 0.114 for the concentration of the acid originally. So now anything else we do in the titration, we can always know that the original concentration was that. Alright, so in the second part, they say after addition of 30 milliliters, so the same titration, just at a different time, probably before the equivalence point, the pH was 4.5, and they want to know what the Ka of the acid was. So since we're looking for at pHs at some time in the titration, remember that's a good time to draw a before and after table. So I'm going to do that. Now that I have the reaction drawn out, we can plug in our quantities. Remember, it's the same titration, so the initial concentration of HX was 0.114, but since we want to do moles here, we're going to go back and use the mole amount. And so I'm going to need to multiply my 0.114 times the volume. So that mole amount is going to be 0.0025, which shouldn't be surprising. It was the same mole amount as the sodium hydroxide was at the equivalence point. The sodium hydroxide, however, is not going to be that, because we're not talking about the equivalence point anymore. We're talking about before it. So we've got to multiply the 30 milliliters, the 0.03, times its initial concentration, which is 0.05. And I get 0.0015 moles, less than the HX, which will make sense since it's before equilibrium. Of course, the before the equivalence point, the NaOH will be 0, and the HX is going to go down to 0.0010 moles. These two are going to go up to 0.0015 moles each. Now you notice right away that we have an amount of the HX left and we have an amount of the NaX left. This is definitely a buffer. How do we solve buffer problems? You guessed it, the Henderson-Hasselbalch equation. So pH equals pKa plus the log of the concentration of the base divided by the acid. And we'll plug in all the values. Now you'll notice we're going to be able to solve for that pKa, and that'll let us get to the Ka. When I plugged all in my values and solved for the pKa, I get 4.32, and then when I anti-log it, I get 4.74 times 10 to the minus fifth. And you'll notice that that answer matches our key. So it looks like that's an appropriate approach. So compartmentalize your thinking and you can make your way through it.